In the previous module, we were looking at calculating standard deviation. And at the time, I told you standard deviation is basically how spread out your data is. And we had mentioned that a small standard deviation means that the data is not very spread out, it's really clumped together. A larger standard deviation indicates that your data is more spread out. And then I said, well, we're going to discuss a little bit more later on how to be more specific about that. And that's what we want to do now is we want to talk about what if your data is normally distributed, which a lot of data actually is in populations. And so normally distributed, we mean if we looked at the histogram would look sort of like this, where the mean of your data set is right here in the middle, and most of the data is clumped together near the mean. And the further out you get from the mean, the less data there is. So if we think about this in terms of, let's say, height, if we were looking at males in particular, male adults, then the average height would probably be somewhere around 5 foot 10 inches, or somewhere in that ballpark. And yeah, there's going to be a lot of people that are 5 foot 11, maybe even 6 foot, maybe 6'1". But that's when we start to get kind of over here. Is there's gonna be a lot of people at 5'11", a bunch of people at 6 foot, some at 6'1". But as we start to get to 6'2", 6'3", there's a lot fewer. And in the other direction, the same thing. 5'9", that's actually where I am about. There's a lot of people in that ballpark. 5'8", not as many, but a decent amount. But as you start to get down to 5'7" males, 5'6" males, there's a lot fewer of those. And that's what we're kind of looking at when looking at a normal distribution. The empirical rule gives us a good estimate of what proportion of people are going to be in each of these groups. So what it tells us is it says if you go one standard deviation above and below the mean, so standard deviation, we'll go ahead and use sigma to notify that we've gone one standard deviation in either direction. Let me go ahead and do this. We're going to say within this yellow region here that's shaded in, that's going to be about 68% of the entire population is in that group there. It then goes out further to say if you wanted to go two standard deviations in each direction, so we're going to go another standard deviation in each direction, then if we wanted to go that far out, we'll go ahead and use green for this. So that includes all of the 68% that we had before, plus these others. Then in that little green area, we'll put a little mark down here, then about 95% of the population is going to be in that green chunk there. And if we went one out further, that if we went all the way out to 3 standard deviations away from the mean, so we got another standard deviation on each side. So if we want to go that far, then this tells us that if I want to color that in as well as all the green, as well as all the blue, or sorry, the yellow rather, then inside of all this purple stuff is going to be about 99.7% of the population. Now this line continues out in each direction so that there's a little bit over here and a little bit over here, but not very many. These are the people that are going to be, like we're talking about height, these are your 7'6" people, your 7'7" people that are way above what we would normally expect. But they exist. There's not a whole lot of them. They constitute about 0.3% of the population. Now, how we're going to use that idea, this is the empirical rule, which is sometimes called the 68, 95, 99, 7 rule. This problem tells us engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean of 5.9 inches and a standard deviation of 0.9 inches. And we want to look at, all right, what range of head breadths can we look at that would fit 68% of heads in this clientele? And so if we think about what that means in terms of the empirical rule here, that would be our yellow region. 68% would be our yellow region, which is to say we can go one standard deviation below the mean and one standard deviation above the mean. So if 5.9 is the mean, then if I want to look at below, then I would take 5.9 and subtract one standard deviation. and that would give me 5. And if I wanted to go 1 standard deviation above, then I take 5.9 and add 0.9. And so if we look at between 5 inches and 6.8 inches, then 68% of people would fit in that range. So that was a pretty straightforward application of the empirical rule, in which we could just straight up look at it and say, all right, we were just told 68% is within 1 standard deviation. It can get a little bit trickier though. So in this case, a company has a policy of retiring company cars. This policy looks at the number of miles driven, purpose of trip, style of car, and other features. The distribution of the number of months in service for the fleet is bell-shaped, so it's a normal distribution, and has a mean of 37 months and a standard deviation of 11 months. Using the empirical rule, what's the approximate percentage of cars that remain in service between 59 and 70 months? So this is a little bit trickier, but what we're going to do in a problem like this is we're going to draw a picture to see what's going on. So we're going to draw our normal distribution, and we're going to look at the mean. So let's go ahead and draw a horizontal line here to help us out. The mean was 37 months. So if we want to use the empirical rule here, we're going to look at 1, 2, and 3 standard deviations away. Our standard deviation was 11 months. So 1 standard deviation would be up to 48, another one would be up to 59, and another one would be up to 70. And so this particular problem is actually asking us, for this probability here, it's asking us what percentage of cars are going to be still remain in service between 59 and 70 months. So the answer to the question is going to be this chunk here. So what we can do is we can go ahead and look at what the empirical probability or the empirical rule tells us. So the empirical rule told us that between these middle two bars is 68%. So if there's 68% evenly distributed between those two bars, then we could say it's 34% in each of them. Now, if we continue that reasoning out, remember that if we looked within 2 standard deviations away, within 2 standard deviations was 95%. But 68% of that is already accounted for in here. So if I want to know what those 2 bars are that are just outside my 34%, their total is going to be the 95% minus the 68% that we've already accounted for. So if we look at 95 minus 68, that's going to, using a calculator off screen and hitting the wrong buttons. That's going to mean there's 27% that's spread out between those 2 bars that are blank that I have in turquoise. If there's 27% split between them, then each one would be half of that. And half of 27 is 13.5. So each one of those is 13.5%. But now we can go out to the third one. So if I go out to the third one, I gotta find a different color here. Here's a different color. If I go out to the third one, then within this purple here, so within the purple, I know is 99.7. But if I subtract off the turquoise, and the turquoise, remember, was 95%, then that means there's 4.7% split between the 2 outside ends, so just at the between 2 and 3 standard deviations away. But that's going to be this one I put an X in, and this one that I put an X in. So if I want to find out what just the yellow one is, I need to divide that by 2 to get 2.35%. That's going to actually answer the question of what's in the yellow, because we're going to get 2.35% there and 2.35% there. That's going to be the answer to the question, because that's what we had shaded in yellow. But hopefully you saw the strategies that I used in this problem here of first of all drawing out the normal distribution and labeling it with, instead of just labeling as mean and 1 standard deviation and 2 standard deviations, labeling as how many months in this case. Then I could draw where the answer was going to be. Then I could start calculating what that answer is.